All right, well, good afternoon. This afternoon, we're going to talk about streaming data. So my name is Alan McGinnis. I am a solutions architect here at AWS, and I work primarily in our streaming data space, which primarily is Kinesis. I work with a lot of customers who do other streaming data technologies as well, such as Kafka, but for the purposes of today, it's going to be focused on Kinesis. With me is Gabriel Como from Comcast, and he is going to talk to you all about how they have leveraged high-speed performance data at Comcast and some of the learnings that they found in the platform that he's created. So I'm going to jump in some of the details, and then we'll invite Gabriel to come up here in a few minutes to jump into the Comcast details. So this is a quick view of what we'll be talking about in the next 45 to 50 minutes. We'll hopefully have some time at the end for Q&A, so when we get there, there's a couple of mics. Feel free to get behind the mics and ask some questions of us. But what we'll do is a streaming data overview. I want to make sure just we're all on the same page for what we're talking about with regards to streaming data. We'll do a very quick interactive demo. We're going to do that here at the beginning, just to kind of highlight what it is that we're talking about with streaming data. Then we'll do a very quick introduction to Amazon Kinesis and the 4 services that make up the Kinesis set of services. And then we'll start talking about consuming from Kinesis streams, because there's 2 different ways you can do this, and each of them have their pros and cons. So I want to make sure we jump into that and you understand which model might be best for you. And then Gabriel will come up, and he'll talk about Comcast and what they have done in the Headwaters platform. He's generally built a platform for streaming data across all of Comcast. And he will dive into the details of considerations for scaling your data streams, and then the impact that enhanced Fanout, which is one of the 2 different consumer choices that you get when you use Kinesis streams, what impacts that had on their architecture. All right, let's talk about the value of data. And this is why we stream data. But let's just quickly talk about the value of data and how that data loses value quickly over time. On this chart, and this comes from a paper produced by Forrester. The author's name is Mike Gallieri. It's a good paper called Perishable Insights, where he talks about the insights into your data is perishable, meaning over time, it decays, or the value of what you can get out of that data diminishes over time. So in this chart, we look at, on the left side, the things called time-critical decisions, those blocks. Time-critical decisions typically happen in real time, so milliseconds after the data was created, or in seconds or minutes. This is all going to be very dependent on your application, but in some cases, seconds or minutes is fast enough for your use case, but can still be considered a time-critical data piece. Traditional batch processes, some of the historical data that you might use or might have, they generally lose value over time, but still have a lot of value, just not value that you can generally use to make a time-critical decision. A very simple example, and probably some of you have experienced this since you got to Las Vegas, you swipe your card somewhere and you get almost an immediate text message or notification from your credit card provider, right? They've got some kind of real-time analysis happening on all the transactions in their cards, and they're looking for fraudulent activity. They might say, oh, suddenly you're in Las Vegas and your card has been swiped at this ATM to get out a bunch of cash, or you use it at this restaurant, whatever it might be, and they've alerted you, and you can reply, yes, it's good, or no, that wasn't me. So that's like a real-time decision that they want to know about, because if it wasn't you, obviously, they want to take care of it. If it was you, then all is good. But they still do batch processes, right? They still send you an invoice at the end of the month, and you still have to pay whatever it was you charged on your card. Now, they could have waited until the end of the month to say, out of these 100 transactions, 3 of them look anomalous, and you can then kind of go through all the different transactions and decide which ones are good or bad. But that's not good for them, not good for you. So it's much more important for them to make that time-critical decision on that data as soon as it gets created. So how is this happening? Through streaming. Those transactions get streamed. Streaming means ingesting the data as soon as it gets generated, processing that data on the fly, and then doing some kind of analysis, doing anomaly detection on it, some kind of machine learning, doing alerts or actions as soon as you learn something from that data. So this whole thing is what we're calling streaming data. And there's different technologies to enable this. But the concept is streaming data. Who can remember the day where you would probably put data into a database from your application, and then you didn't do any learnings from it until a batch process ran that night, or a batch process ran at the end of the week to move that data into some warehouse where you could then go run reports? I'm pretty sure probably pretty much everybody could put their hand up to say, yeah, you used to do that, or you still do it. Because, like I said, there's still plenty of use cases where that applies. But to get those real-time insights, it's important to ingest that data as soon as it gets generated and then analyze it immediately. So common use cases of streaming, these are just a few. And I'm not going to talk about them all in detail, but the two that we see very, very popular are log analytics, feeding into data lakes, and then I'll say IoT analytics, but I'm going to generalize IoT analytics. It's not quite IoT devices, doesn't necessarily have to be temperature sensors or pressure sensors. But I will call an IoT device just a connected device, like your phone, a game that's running on your phone. These are connected devices that are always sending data. So between those three on the right, they generate a ton of streaming real-time data that our customers are using to get real-time insights out of them. And in the industrial automation space, we have plenty of customers in the factories who are using streaming data to get insights into what's happening across their operations in near real time. Imagine they want to know if one of their lines is down or is taking longer to process some product than it typically does. They want to know that right away. They have to go in and fix it. So that's a good example there. So how do we do this at Amazon? We have 4 different services for streaming data. This is probably old news to you. Maybe a quick show of hands. Who are already using a Kinesis service in production today? So it's about maybe a third of the room, but that's a third to a half of the room. So very good. So I'm not going to get into then a ton of details about what these services do, but I am going to tell you some of the differences between them and why you might choose to use one over the other. I'll start on the left, Amazon Kinesis Video Streams. This is a relatively new service. We launched it at reInvent last year, but it enables you to ingest and process binary encoded time series data. So that could be video, audio, LiDAR, radar. It's intended, we call it video because video is kind of the number one use case, but there's other binary formats that can easily be ingested into video streams. The other 3 services, and what we're going to focus on mostly today, is our data set of services. So these are the types of services that are just receiving either unencoded or encoded data that's coming off of your systems. Could be log data, could be application event data, being sent into Kinesis so you can get some of that real-time analysis that we just discussed. So the 3 services on the right, data streams, data firehose, and data analytics, can all work together to get you those insights. Kinesis data streams, to compare and contrast it with firehose, I get that question a lot. Kinesis data streams, I'll tell you the biggest question that you can ask yourself to determine should I use streams or should I use firehose is this. Kinesis data streams requires you to typically write custom code to get data from the stream. So you have a data producer that puts data into the stream. It's going to sit there in a buffer, by default 24 hours. You can extend it up to 7 days. And then your consumers, 1 or more, are going to take the data off the stream and do something with it. So in that context, the stream is just a buffer, and you have to write the custom code to take the data off the stream and apply your business logic to it. The stream doesn't care if the data was used or not by your consumer. Once that window expires of 24 hours, which is the default, the data is gone from the buffer. So it's a little bit different than a queue. Like with a queue, if you're using something like SQS, you can pop a message off the queue, and it's no longer going to be consumed by any other queue consumers. With a stream, it's going to sit there until it expires. Now, with Kinesis Streams, you're also writing your own code to take the data off of the stream. And that contrasts a little bit with Firehose. Firehose, yes, the front end, how you get the data into the Firehose is very similar. It's going to be an agent, perhaps, that's running on your local host that's taking log files and streaming the logs into Firehose, or you're using the SDK to write messages directly into Firehose. But the biggest difference is Firehose has a managed consumer to take the data off of the streams and put it into one of 4 different destinations. You can put it into S3, put it into Splunk, put it into Redshift, or put it into Amazon Elasticsearch service. So when you ask yourself, I want to stream data, I don't really want to do much with it, at least not yet. I just want to put it into S3 so I have a durable store, relatively inexpensive spot to put my streaming data. Firehose by far and away is going to be the easiest way to do it, and it probably should be the first consideration you'd make. Now, there's a lot more complexities there. You can do things like data transformation with Firehose using Lambda. So there's a lot of more complexities that I'm kind of glossing over. But if you're asking yourself between streams and Firehose, and you ultimately say, I really just want to stream the data and put it into Elasticsearch so I can do log analytics in Elasticsearch, and I don't really have to transform my data in the middle, consider Firehose. The last service on your right, Kinesis Data Analytics. This service gives you the capability to do real-time analysis on that data before it even persists in any destination. So it's basically an application that can listen to the streaming data, get some insights that you have to code. You have to tell it what insights you want. So we have 2 versions now of Kinesis Data Analytics. One is SQL-based, so you can write some SQL code to do things like tell me how many times this event has occurred in the past 2 hours. I'll give you an example. We work with an e-commerce customer, not Amazon, a different one. And they use Kinesis Data Analytics to find out what the top selling products are in a 30-minute window on their website. So they stream all the order data through Kinesis Streams. They run Kinesis Data Analytics, which inspects that streaming data, and they run an aggregation every 30 minutes. And then they save that out to a dashboard so their business users can go in and look at the most popular ordered products over those windows, and then they can make decisions about how they want to increase promotions on the website for other products that they want to perhaps get higher in the sales rank. So that's just a quick overview of those 3 services. And we'll move now into a bit more detail after we do a very fast demo to kind of put it all into perspective. OK, so I need you all. This is an interactive demo. I need your help. I want you to pull out your phones and go to that URL. Don't do it on your computer. You could. It's just not going to be as valuable. Please use your phone. I'm leaving it up for 1 second to give you guys a chance to pull it up. What you should see is a quadrant with a number of boxes, or sorry, a quadrant with a ball. You can move the ball around. And I have a window somewhere. There we go. OK, so this is all happening in real time. This is a real demo. I'd like everybody to try and move the ball into quadrant A. Move the ball into quadrant A and then hold it there. And we should see within 3 to 4 seconds, this should all show up in A. Yeah, very cool. We're also capturing some other numbers, so about almost 500, yeah, over 500 of you now have participated. That's uniques on the top. And then it's numbered the raw data about how many are in each quadrant. I said A, but we have a couple of non-conformists. That's OK. So let's all go to C. Let's all move it to C. Hold it there. Should be 3 to 4 seconds. We should jump it. There we go. Come on. There we go. OK. So pretty cool. So this example just highlighting kind of this could be anything, right? This could be your business KPIs. This could be log data. This could be errors that are streaming from your application error logs. But you can take that data, use Kinesis Analytics, use Kinesis to ingest it, get very real insights out of it, and put this on a dashboard for your business users. Of course, per 1 second might not be necessary for some of those types of things I just mentioned, but you can, of course, change the window to be every few minutes, every hour. This is just a good one to show you for how fast we can do it. Last thing, we're also capturing device data. So iOS to Android, not uncommon, slightly higher on the iOS. No Windows Phone users? There is a funny point on that because I did this at a previous talk, not here at reInvent, but it was at a different session, and it did show up. There was a Windows Phone. And I asked the person in the room to put up their hand to volunteer, but they did not. All right, let's go back to here. All right, cool. All right, I'll figure this out here. There we go. OK, this is the architecture of what you guys just did. I don't have a whole lot of time to spend on this. We have to kind of jump through and get to the next section. But the nice point about that whole demo is that it was all serverless. So there's no EC2 instances in the mix, nothing to manage on the back end for servers. It was all just Kinesis and Lambda and DynamoDB, and of course some static content in S3 for the JavaScript and HTML. So a very simple application, and in fact, it can even be improved because since this demo was built, there have been changes to the Kinesis Analytics product. I don't know if I have a laser pointer that'll actually work. Anyway, you can see here after the Kinesis Analytics application and before the Lambda function, there's this extra stream, this Kinesis aggregate stream. That can be removed now. In fact, there's a feature that's been released that allows Kinesis Analytics to invoke a Lambda function with the results of its analysis. So I could take that piece out, and it's even a simpler architecture. But what we're really here to talk about today is high-performance data streaming and how you can best do that on Kinesis, particularly with Kinesis data streams. Before we do that, we want to talk a little bit about producers and consumers, because we're primarily going to discuss consumers today. But I want to make sure we're all on the same page. There's plenty of ways to produce data to Kinesis, plenty of ways to consume. I am definitely not going to go through each of these. The point I want to make on the consumer side of it is the Kinesis client library and AWS Lambda. Those are the two that can most benefit from some of the features that we're about to discuss. The other ones that you see here, what am I looking at here? Like Apache Flink, Apache Storm, Apache Spark, they can also benefit from some of the new features, but it will require the open source libraries to use some of the new APIs that we have created that I don't believe they have yet. So, talking about consumers, I have a clicker here. I should use it. Standard consumers. This is what the vast majority of stream consumers on AWS are using right now, and that's because it's been the only way to do it up until about August. So what is a standard consumer? Actually, before I jump into that, take a look at this, the kind of the white rectangle in the middle. That is the representation of a stream that is made up of shards. If you're not familiar with shards, a shard is essentially a unit of scale in a stream. It can accept 1 meg per second or 1,000 records per second. So when you do your analysis of a Kinesis stream and you have to determine how many shards, or sorry, how much data you want to ingest into that stream, that determines how many shards you'll have to put into that stream. So if your use case says that you're going to stream about 4,000 records per second, you will need 4 shards in your stream. So a shard is a unit of scale in a stream. A consumer application has multiple threads. Each thread gets data from a shard via a getRecords call. This is largely abstracted from you if you're using one of our libraries called the KCL, the Kinesis Client Library, or if you're using Lambda to consume. The getRecords operation is abstracted by those libraries or the service, but it's important to understand what's going on so that if you consider the KCL 2.0, which is the next version, or the newest version of Lambda, so you can use enhanced Fanout of Kinesis, which gives you that lower latency. So this is what's going on. getRecords is made, and data is returned. Come on. My clicker might be dead. Oh, you have to press it a whole bunch of times. OK. So the getRecord operation can only be made 5 times per second on a single shard. That's a limitation in the service, and it's not something that can be changed. And data can be returned at a rate of 2 megabytes per second per shard. Also, that's a limit from the service, not something that can be changed. So with that, the fastest that your consumer can get data from the stream is every 200 milliseconds. This is a polling operation that your consumer application has to implement, or the KCL will do it for you on your behalf. But get records every 200 milliseconds, because you have to stay below that 5 requests per second for the get records call. If you go beyond that, if you lowered it to every 100 millisecond of a polling window, that's 10 times per, and 5 of those would get throttled. So the service, the Kinesis service, would return an exception, and your consumer would have to swallow that exception, do a little bit of a back off, and retry. So 200 milliseconds is not bad. In many cases, that's good enough for real time. Like I said earlier, it all depends on you and your company's definition of real time, but it's not bad. But what if we do this? What if you have 5 consuming applications, all of which have different business logic, perhaps different teams in your organization that want to do something with the data? Now, each of them can only get 400 kilobytes of data each, because it's a 2 meg per second egress limitation on that shard, and they have 5. So that means they can only get 400 KB. And they can only ask for data once per second, because with 5 of them, they don't want to go beyond the 5 requests per second. So they can all only ask for data now once per second. So now your latency is going to go up. For the previous use case with one consumer, it could ask every 200 milliseconds. These can now only poll every single second, so your latency for how quickly your consumer can respond to data in the stream, it goes up. So now with enhanced Fanout, we've changed that model quite considerably. This is a new feature, like I said, launched in August. And we've introduced some new APIs to take care of a lot of the issues that we just described. So there's a few new APIs. The first point to make, it's the subtitle on here, is consumers no longer poll. Messages are pushed to your consumers as they arrive. So the server will push them over a long-running HTTP2 request that has been made by the consumer over a subscribe to shard API call. So the consumer initiates subscribe to shard. That will remain open for up to 5 minutes. It uses HTTP2. So how many people here are familiar with WebSockets? A lot of you, that's great. So this is not WebSockets, but if you know what WebSockets does, this is very, very similar. It's just managed by the protocol itself. It's not a layer on top of HTTP 1.1. It's managed by the HTTP2 protocol that allows the server, in this case, the Kinesis service, to send data out of order to the client without having to be asked for each packet. So, come on, there we go. So this, it's hard to see, there's a little curly brace in between the data producer and the stream. That's our piece of data that's coming in. The shard will persist it, and then it will send it to the consumer application right away. I'm going to have to go back to the keyboard. And then it will keep doing it over and over and over again for as long as data is being sent to the stream. So that means your data is now, your consumer is now getting that data very, very frequently, on the order of 50 to 70 milliseconds after the data was written. It's being delivered to your consumer. Contrast that with the best case in the get records operation was about 200 to 300 milliseconds. We're now down to about 50 milliseconds latency. That's much better. That's only with one consumer using the get records model. When you had those 5 consumers using the get records model, right, you're talking about one request per second, so much longer latencies. The other big benefit is that each consumer gets its own dedicated 2 megabytes per second of egress. So each consumer has to say register stream. We create internally this pipe, EFO pipe, that gives it its own dedicated throughput. And so now when it comes back and calls subscribe to shard, we give it its own 2 megs per second egress limit just for that one consumer. And so it's no longer having to contend for that 2 megs per second per shard limitation that previously existed with the old API. I can now come in and add more and more consumers. The data will be pushed to the consumers, and they can get the full throughput from the stream to the consumer. So no more contention for 2 megs per second, no more contention for 5 reads per second. So it really enables you to add more and more consumers to a stream and not have to worry about contending for resources, where you did have to definitely consider that in the older model where you're doing get records. So when should you use standard consumers? That was the first one that's calling get records. If your total number of consumers is low and your consumers aren't particularly latency sensitive, then consider using the older model. Our library, the KCL, we have 2 versions, 1.8.x and 2.0.x. 1.8 is the older one. We've upgraded to 2. I would recommend you all use 2.0 because it supports both. You just have to implement different interfaces for the consumption model that you want to implement. But if your consumers aren't latency sensitive and you have a low number of consumers, consider using the standard consumers. And it's also going to be cheaper. There are cost dimensions with the enhanced Fanout feature. So we will charge you for those pipes, these EFO pipes on the previous slide. And there's a per gigabyte data egress now in that model. So it's cheaper to use the old consumers, which is why if you have very few consumers with low latency requirements, use the old way. When to use enhanced Fanout? Multiple consumers, let's say more than 3, and you have very low latency requirements for that. If you have low latency requirements, less than 70 milliseconds, then enhanced Fanout is how you're going to get there. And that does it for me. So I'm going to hand it over to Gabriel now, and he's going to take you through what they did at Comcast. Sorry, my apologies. My screen up here is a little different. There we go. Thank you. Thank you.
All right. So 100% of the Kinesis users that I have worked with so far are either overpaying for the Kinesis streams or facing technical difficulties because their stream is underscaled. So how do you scale a Kinesis stream, and how does the new enhanced Fanout consumer changes the pictures? Hi, my name is Gabriel Como, and I lead the streaming data platform at Comcast. I'm really excited to be here. I hope you guys are enjoying the AWS reInvent 2018 as much as I am. And so I will split the rest of this session into 3 parts. First, I'll give you some background and some context about the streaming data platform that we've built at Comcast. Then we'll see 5 considerations to think about when considering scaling a Kinesis stream. And finally, we'll see how the consumer Fanout, the new feature, changes this picture. So before we start, I've got a good news and a bad news. The bad news is that I left a lot of math on the slides. The good news is that I will not be boring you through those. Instead, I will focus on the principles and the logic to arrive to those formulas. And I left them so that if you want to dig further into this topic after the talk, you have the material to do so. The second good news is that we actually implemented those formulas into a calculator that we recently open sourced. And I'll come back to that towards the end of the demo. Of the session, sorry. Over time, we came to call the concept of managing the stream data centrally a streaming platform. Jay Krebs wrote that in a blog article in 2015, actually that first link that you see on the slide. And Jay Krebs and his team are the one who built Apache Kafka while they were working at LinkedIn. And I really like this quote because it marks to me a transition in the industry where streaming really took off. It's to me a paradigm shift because data is not a table in some database anymore. A data set is alive and changing, and it has a whole new dimension when you consider streaming. So I added 2 articles that are excellent and I think fundamental for any engineer working on streaming. I would highly recommend you to go through those if you haven't read them already. So we called our streaming data platform at Comcast Headwaters, And there are three objectives that we try to accomplish. The first one is that we want to decouple the data producer from its consumers. So the teams that write the applications that interact with our platform are from different divisions within Comcast, possibly even from different companies. And therefore, it's important to, so because they are from different divisions and companies, they have different objectives and different budgets. So it's really important to us to have as loose as a coupling as we can between those various applications. Also, the platform acts as a buffer in case one of those applications isn't available for some time. It doesn't affect the other application, or at least as little as possible. And also, it formalizes the data exchange between those applications. So not only from a technical point of view in terms of API and data serialization, but also in terms of processes such as data governance and data security. The second group of objective is to assist the data team with their streaming needs. So we help them scale the Kinesis or the data stream appropriately. We help them manage the data retention and onboard consumers. Finally, and really importantly, we want to foster real-time data exchange within the company. That's really important to me because I believe that data is one of the most valuable assets that a modern company can have. So we want to lower the bar of entry as much as possible so that teams can share the data that they have. So to that end, we manage the metadata about the stream to answer questions such as who, when, how. And also the data set, whether structured or unstructured, are associated with a schema. And that schema evolves over time. So we manage that so that the consumer team can make sense of the bytes that flows through our platform. Finally, we implemented what I call a fair cost model, in which the teams that benefit from the data are the ones that finance the infrastructure to power those data exchange in proportion to what they use. I don't have time to dig further into this, but this is a fascinating topic, actually. To give you an idea of the scale of our platform, we have hundreds of data streams, and combined they generate millions of events per second or gigabytes per second. So this is a high-level overview of the architecture of Headwaters. It's composed of three main groups of components. The first one on the upper left is the CI/CD pipeline created that uses the AWS services that you typically use to build a cloud-native application. It creates the Headwaters control plane, which is essentially based on that pattern with API gateway, Lambda, and DynamoDB. We use other services where it makes sense, such as SSM or SES. And also for troubleshooting and monitoring, we use CloudTrail, CloudWatch, and X-Ray. Now, this control plane is the one that creates the data stream. So obviously, the data streams are mostly focused around Kinesis. But also, we create an SNS topic that we associate with each one of the data stream so that the stakeholders of the stream have a communication channel to communicate about that particular stream. So the stakeholders of the stream are us, the platform, the data producer, and the data consumers. So for example, if we detect that there's no data incoming into the particular stream, we may raise an alert on that topic. Or if the data producer is planning to perform some maintenance on the producing application that may impact the availability of the data, that team may use that topic to communicate that. So in order to understand better how our platform works, this is a flow diagram of how a data producer is going to create a stream. So first, the data producer requests the creation of a stream to our Lambda function via the API gateway. The Lambda function is going to create the appropriate resources, the Kinesis stream and the SNS topic, and also is going to register the user to that SNS topic. Then it's going to use IAM to grant the appropriate permission to the user. And finally, we'll send a welcome email with further instructions on how to proceed. At this point, the data producer can write data to the Kinesis stream, can monitor the streams using CloudWatch metrics, and communicate with the other stakeholders. So now, let's see 5 considerations that I think you should keep in mind when scaling a Kinesis stream. Number 1, the data producer limit. So Alan just went through that. Do you remember what those 2 limits? There are 2 limits, hard limits that you cannot change about the data producer. Do you remember what those are, the 2 limits? Yeah, so the 1 megabyte per second per shard and 1,000 put requests per second per shard. So let's see how this translates into a real life scenario, a real life use case. Comcast users can watch TV, live TV, or on-demand movies through the internet. That's video over IP. And there's a number of devices that they use to do that, whether mobile devices such as iOS, Android, desktop application, or IP set-top boxes. All those devices report analytics data back to our platform in a single stream. And this is one of the most valuable streams that we have within Comcast. There are literally a dozen different teams that are consuming from this data set. And they range from business intelligence group wanting to report usage of the service, to operations team who needs to monitor a specific part of the system, to data scientists, to data engineer who may process the data as it streams through. So they may filter, enrich, or sessionize the data. And they usually send the data back onto our platform. So this is what the actual usage of the stream looks like. You see the bandwidth or the throughput over 4 days. So as you may expect, you have the usage going up and down as people, our users watch more TV throughout the day. The usage increase, and it peaks around dinner time and a little bit after that, and then falls back down when users go to sleep. So with a little bit of history, you can easily compute the average and the maximum bandwidth. What I would like to draw your attention to are those bandwidth surge that you see. And those happens because we have hundreds of thousands, millions of devices reporting analytics data, and they may react to a particular event and generate a surge of traffic like that. For example, an EAS alert would trigger such an event, or if you have a popular show, say the latest episode of Game of Thrones, or the Super Bowl might have a surge of traffic like this. So when you think about the 1 megabyte per second per shard limit, you have a choice here. What bandwidth are you going to use? And this drives to what I call this back pressure scale, where you have to use at the minimum the average bandwidth, and you can use all the way to the maximum bandwidth. If you use the maximum bandwidth, you'll see it's going to be a little more expensive because you have more shards. But if you use the average bandwidth, you'll have more latency in your data. Now, dealing with back pressure is actually pretty difficult and expensive. So you have to consider the whole picture when you're looking at the cost. And so I would strongly advise you to look at the maximum bandwidth for the period of time that you're dealing with. If you, whatever bandwidth you use, you need to deal with back pressure because you can always have a new usage that goes over your historical maximum. So you have to deal with that. If you don't, guess what happens? You get exceptions, right? And you're most likely to lose data. So this drives us to the first slide with the formulas. Because you have those 2 limitations, you have 2 formulas. When you look at those 2 together, you see that if your messages on average are smaller than 1 kilobyte, then the throughput limitation is what's going to drive the number of shards. So what you do in that case is very well documented in the Kinesis documentation. You do record aggregation. Essentially, what you do is you batch records together before sending them to Kinesis, and the KPL does that for you automatically. So That will drive you down to the first formula where the bandwidth is the limiting factor and is driving the number of shards. So what you do in that case to lower the number of shards that you still need is to compress the data. So the providential part about this particular slide is that as I was writing this very slide a few weeks ago, I was contacted by a team within Comcast who had a problem. They were seeing exceptions on their stream, and they kept scaling up their stream until they reached 700 shards. And they were concerned about the price of running that stream. So I looked at their stream, and sure enough, they were generating a lot of small messages. So I gave them the two pieces of advice that I just gave you: aggregate the record, compress the data. And they were able to drive down the need for the number of shards from 700 to 80. And more importantly, the cost of running their stream, they saved about $200,000 per year. So I hope that this advice is going to be as beneficial to you as it was for them. Now, consideration number 2, the limit on the consumer side. So again, Alan talked about that. Do you guys remember what those are, the 2 limits? Right. So the first one is that the consumers as a whole, as a group, are going to share 2 megabytes per second per shard. And similarly to the producer, this gives us this formula. Now, the second limit is that the consumers, again, as a group, may not request more than 5 GET requests per second. And so this is problematic because you cannot solve that particular limit by increasing the number of shards. That's because it's related to the frequency at which you query those shards, no matter how many they are. So you have 2 groups of solutions to this problem. The first one, on one side, is to try to solve this problem on the client application side. So if you control all the consumers, if you can dynamically adjust the frequency at which you request the GET record for the stream, and if your consumers are aware of the other consumers in the group, then you can solve that problem. So as you can see, this is pretty challenging to do. And also, this is naive anyway, because you can still have a consumer that would be a rogue consumer that hogs all those requests per second and basically performs a denial of service attack on your stream. So the other categories of solution is to have a different architecture on the server side. So one of the ways to solve that is to create a copy stream, a slave stream. You do that by using Lambda or Kinesis Analytics, and you spread the consumers across those 2 streams. The downside of this solution is that the reliability of the slave stream is lower than the master stream. So you can think about other architectures that you can create in order to solve that problem. Now, consideration number 3 is to look at how Kinesis actually works to scale a stream up and down. So let me illustrate that with an example. Imagine that you have a stream that has 3 shards and a data retention of 1 day. Kinesis has only 2 operations that it can do. It can either split a stream into 2 or merge 2 shards into 1. So now imagine that on day 3, you split shard 1 into shard 3 and 4. Shard 1 at this point is going to be closed. So you will not be charged for that particular shard. However, the data that it had been receiving up until that point are still stored onto that shard. And they're going to be stored for the duration of the retention period, right? So only 24 hours after you do that split operation, the stream is going to actually remove shard 1, and you're going to end up with a 4-shard stream. So let's talk about something a little different here. How does Kinesis know what shard to write the data to. You guys know? It uses the key, right? So when you send a piece of data to Kinesis, you send the data associated with a key. And based on that key, it will determine which shard the data is going to. So there are two types of keys. Either your key is perfectly balancing the data amongst all the shards, or it's not. If it's not, what's going to happen is that some of the shards is going to receive more data than the others. And this is going to create hot shards. In that case, you want to split those particular shards, the goal being that each shard receives the same amount of data as much as possible. So this is a little difficult to manage, actually, and unless you have a good reason to do that, I would recommend you to use a key that spreads the data evenly across the shards. And if that's the case, what you want to do is use that update shard count operation that Kinesis provides. And it's a convenience method that basically uses those split merge operations that I mentioned in order to create the number of shards, the appropriate number of shards, and maintain an equal portion of the key space for each one of those shards. And so if you observe Kinesis scaling from 3 shards to 5 shards, you'll see that it goes through a bunch of steps, actually following this pattern of split, split, merge, until it creates the shards that you need. As you can see, it creates a number of temporary shards, and because those operations are synchronous, you see that it may take some time, especially if you have a lot more shards than this. So now, let's see consideration number 4, the consumption speed. So it's unfortunate, but in my experience, it happens from time to time that a consumer comes to you and says, I cannot process the data fast enough. You need to scale up the data stream. So obviously, and that's because they have data processing on their side that is taking a lot longer and so creating a bottleneck. So the appropriate solution to this problem is to re-architect the consumer so that you basically take that bottleneck into a second layer that can scale independently from the layer that is consuming from Kinesis. So in the example that I have on the slide, so you have a 3-shard stream. Each shard is receiving 1,000 messages per second, but consumer number 2 can only consume 500 messages per second. And so because the stream has 3 shards, the consumer is bounded by having 3 consumer processes. So again, the solution here is to re-architect consumer 2, but the thing is that this takes time. And so in the meantime, you may have to scale the stream to comply with the request of that particular consumer. But the good thing is that you can put a price tag on how much this costs, and then you can charge this particular consumer as an incentive to do the work. And so this drives you to this formula that basically you have to compute for every consumer, look at how many shards each one of them need. So now the 5th and last consideration is what I call the acceptable data latency. And there are different cases where this can happen. The one that I illustrate here on this diagram are the surge bandwidths that I showed you at the beginning of the presentation. The red line is the producer producing data, and the blue line is the consumer consuming the data. And because of these particular scenarios with those numbers here, the consumers are bounded by a consumption throughput that is lower than what the producer will produce. And therefore, the consumer is going to start lagging. The data is going to have more and more delay, more and more latency. So the difference between the end of the surge and when the consumer catches up is going to be the maximum latency that the data is going to have, that the consumer is going to see. And the point I'm trying to make here is that you can compute the number of shards that you need if the consumer have an SLA, if the consumer have specific requirement on how much that data latency can be at the maximum. So in this slide, I name some variables, and that leads us to this particular formula that looks complicated. It's really not. That you can use to plug the numbers to see how many shards you need to comply with requirements such as this. There are two other contexts that are similar to that. If a consumer is unavailable for some time and suddenly comes back up, it will need time. It will accumulate some lags, and it will need time to catch up with the real-time stream. And again, you can compute how long this is going to take based on various input variables, and most importantly, the number of shards. The other cases where this happens that's similar to this is if a consumer is trying to reprocess past data. And again, you can compute the rate at which that consumer is going to consume data. So for example, it may need 10 minutes to process an hour of data. So with that, let's see what the new enhanced Fanout consumer changes these pictures. So as Alan mentioned and explained, a Fanout consumer have basically a dedicated 2 megabytes per second per shard. And essentially what that does is that it isolates this consumer from the other consumers. So what this does not change is the fact that Kinesis still enforces limits on the data producer, that Kinesis still works the way it does by splitting and merging shards together. And it doesn't change the consumption speed because the bottleneck is not in terms of the consumer reading the data from Kinesis, but it's a little bit further down the stream. What this does change, however, is obviously the fact that the data consumption limits are affected. So the Fanout consumers see no limits because they can consume twice as fast as the producer can produce. And it changes also the other consumers, the regular consumers, because now they have a smaller pool of consumers that they have to share that 2 megabytes per second bandwidth with. Similarly, it changes the maximum acceptable latency. And for the same reason, again, the Fanout consumers will see no lag. And the regular consumer have a smaller pool of consumers to share the 2 megabytes per second with. So this is the calculator that we implemented. It is open source. I would encourage you to go check it out. Basically what it is it's a web form in which you input the numbers that describe your Kinesis stream. Things such as the average message size, the average throughput, the maximum throughput, etc. And it's going to recommend the optimal number of shards that your stream should have. It also is going to give you a cost estimate for how much the stream is going to cost you. And also, it supports the new enhanced Fanout consumer, and it will also provide you an estimate for how much running a specific enhanced Fanout consumer will cost in this particular context. So in conclusion, I hope that this presentation has given you a framework to think through how to scale a Kinesis stream. Again, the considerations to keep in mind are the producer limit, the consumer limit, the way Kinesis scales a data stream, the consumption speed, and the maximum acceptable latency. With that, I thank you for attending this talk, and if you have any questions for either Alan or I, we'd be pleased to answer them. Thank you.
Yeah, there's a microphone. If you don't mind stepping to the microphone.
Hello. So in one of the previous sessions, I was told that a shard should ideally be matching with 1V CPU to make it efficient. Is that what you noticed also?
Could you repeat that? I'm sorry.
So shard, when we are like building up the shards, the number of shards. So ideally, one shard should match to one vCPU.
If you're, hopefully you all heard that. With the KCL, if you're building a consuming application using the KCL, then essentially a thread will obtain a shard lease. So it makes the most sense for optimization of CPUs and shards. So that makes a lot of sense. It's not required, but that would be the optimal way to do that. So you may, though, consider having multiple hosts process the same stream. So if you have a very large stream, for example, with, let's just say 400 shards, and you try to consume that with one single host, you're not going to get a box with a 400 vCPU, so you'll have to spread that across multiple hosts, multiple EC2 instances. But the KCL will manage the distribution across the different hosts. Okay.
Related to the topic of the spreading it over multiple hosts, with the enhanced fanout, is the 2 megs per second limited to unique consumer, or is it spread across the application that is load balancing across those hosts?
It is specific for the shard. So typically the single consumer record processor, so similar to that question where there's a thread that is leased to a given shard, it's specific to that.
To that individual thread.
That individual record processor for that singular consumer application. So another consumer application that might come online would get another record processor, and it would get its own 2 megs per second egress.
But off of a different shard.
No, on the same shard.
On the same shard. Okay,
Yeah,
so
so
with
every
enhanced
time-
fanout then.
Every time a consuming application registers, every shard in the stream gets another 2 megs per second specifically for that application.
Even when you're using a shared application group in the load balancing method rather than the multiple unique consumers method.
Well, every time the consumer application calls the register stream consumer API, which it has to do.
Okay.
Every consumer application has to make that API call because we give it an ARN, we give it a unique ID. Once that's done, we provision resources in the stream that gives that particular consuming application 2 megs per second specific to it, which is independent of any of the older consumers who might also be calling the get records. If you have older consumers who are calling the get records operation, they're still going to be limited to the 2 megs per second across all consumers who are calling get records. So only that 2 megs pipe, if you want to call it that, is dedicated to your new EFO enhanced fanout consumer.
Okay. And for the enhanced fanout, where is the data persisted? I know in the regular standard consumers, the KCL uses Dynamo to persist the precision per shard per unique consumer application.
That hasn't changed.
That's still going Dynamo, it just looks slightly different.
Yeah, the checkpointing implementation is exactly the same with EFO. Yeah.
Perfect.
Hi. We use the KPL and get a lot of performance improvements for the record compaction as it puts it onto the queue. If we go serverless with Lambda, is the KPL still going to work that way?
There is a library that you can use in your Lambda function that will essentially de-aggregate the records that were aggregated by the KPL.
Right, but that's on the consumer side. I'm concerned about the producer side.
Oh, are you talking about
Lambda for a producer?
Oh, you're talking about Lambda for producer. I'm sorry, I misunderstood.
Same thing, the library can also aggregate the messages together before sending them.
Yeah.
Okay.
Now you don't get, what it will do is create the same aggregation structure, but it's still a little different than running the KPL locally on a host, because the KPL locally on a host does a lot of buffering, because it's running a separate process in the background, like a C++ based process, which has a local buffer, has a lot of the back off and retry capability already built in. This library will allow you to use Lambda to create the same structure, but you lose some of the benefits that you might get from running like a long-running process that the KPL provides if you're running it natively.
Okay, thank you.
Okay.
For the EFO case and the limits that you guys were talking about, those numbers apply whether you're using the KPL and having aggregated messages or not, right? So it's like 1,000 per second, that's 1,000 aggregated or individual messages if I wasn't using the KPL.
Yeah, the 1,000 records per second. When you do aggregation with the KPL, from the Kinesis streams perspective, it just sees, even if you aggregate 100 of your records into a single Kinesis record,
Yeah.
that appears as a single record in Kinesis, and you could send 1,000 of those over the wire before you'd be throttled by the Kinesis front end. So Kinesis itself, the service does not know that there's any aggregation going on. This is just a buffer. The only things that know about this aggregation are the producer and the consumer. So from the Kinesis streams perspective, it's just a record. Just happens to be made up of aggregated smaller records.
Right, okay. And then from the KCL side, I know that there's a way you can set like max records fetched with each get. That's again referring to like Kinesis messages.
Yes.
Which would be aggregated in that case.
Which may be made up of hundreds of your actual user records that the producer created.
Right, which depends on the load, of course, because the KPL doesn't have like a fixed aggregation factor, right? It's just sort of, I think it's like 5 megabytes, or every so often it will just ship them, right? So
yeah, the KPL, well, it's not going to aggregate more than the maximum amount of records that can go into a single put, which is a megabyte. So
right, okay.
there is a limit, and it does know where to stop aggregating.
Okay.
And you do have some properties in the KPL that say, I only want to aggregate 200 records max. Even if that's well below that 1 meg, you can still make that property setting.
Okay.
1 meg compressed?
I'm sorry?
1 meg compressed?
1 meg compressed. We don't care, so it's 1 meg of binary data. So if that's 2 megs of your own data that you've compressed using gzip down to 1 meg before you send it, that's fine by us. As long as your consumer knows how to unzip it. Yep.
So AWS launched a managed Kafka service today. How
Yep.
does that compare to Kinesis? When might you want to use one?
I was waiting for that question. So I don't know if you guys heard that. So yeah, today we announced Amazon managed streaming for Kafka. So Kinesis is not, and it's owned and built by the same team that built Kinesis. The Kinesis will continue to evolve independently. The reason we built that new service, one of the main reasons, was we have a lot of customers who are using Kafka today in the data center, or even in EC2. And we've worked with them to consider moving to Kinesis, but they're like, we just have too much invested from a development standpoint, a lot of code, a lot of operations, that we just know what we're doing in Kafka. We would love for you to manage some of that for us, but we're just not interested in a migration at this point because we're using some features that you don't support. Log compaction is a good example. You can do it in Kafka, you can't in Kinesis. So in order to get those customers kind of a nice managed solution for their environment, that was the genesis for managed Kafka.
Yeah, this is great. What I would add to that is that Kafka and Kinesis are really two different ecosystems. You have different tools, and indeed teams have a lot of work that they put into their application in order to get to where they are. So it's good to have those two options, I think. This is great.
And we just ran out of time as we are getting hooked from the stage. So thank you all very much.